In this video, I'll be going over alkene reaction part 1. So if we have some kind of alkene like so, and remember alkene means the word double bond, and we react it with HBr, we're going to add a hydrogen and a bromine on this molecule. If we react this with Br2, we're going to be adding 2 bromines, and if we react this molecule with HBr with some kind of peroxide, we're also going to add HBr, but in a different location in comparison to this. So in terms of the mechanism, as we know, we're always going to have some kind of nucleophile attacking the electrophile. And remember, when identifying the nucleophile, it's always probably going to be some kind of electron-rich molecule. So in this case, it's going to be the double bond, because as we know, this double bond has 2 pairs of electrons, thus it's electron rich. So the first step is for this to attack the hydrogen, like so. And when this happens, we're going to get this molecule. So now the question becomes, where does the hydrogen add? Is it added on this position or on this position? And remember that you always want to create the most stable carbocation. And in this case, secondary carbocations are more stable than primary. So because of that, the hydrogen is going to be added on this position, and a positive carbocation is going to be formed here. So now the next step is we have this molecule, and we have free bromine minus charge laying around, right? Because as you see here, this electron is now on the bromine. So because this is the electron-rich molecule, this is now going to act as our nucleophile. So now the next and final step is for this bromine to attack this positive carbocation like so. And when this happens, we're going to get a molecule that looks like this. And if you want, you can also draw the hydrogen, but for now I'm not going to. So here is the mechanism for any hydrohalogenation reaction. So very similar to the previous reaction, the mechanism for this reaction is going to be very similar. So as we know, the first step is for the double bond to attack one of the bromine molecule. So when this happens, we're now going to get an intermediate that looks like this. So very similar to the last problem, the bromine is going to be added on this position so that we can form a positive carbocation on the more stable position, aka the secondary carbon. So now the last and final step is for this free bromine, which is, bromine minus, to attack this positive carbocation because this is electron rich now. So when that happens, we're now going to get a molecule that looks like this. And that is the mechanism for this reaction. So now the mechanism for this free radical reaction involving peroxide is a bit longer than the previous ones. So if we have peroxides and we react it with some kind of heat, the first step that's going to happen is this bond is going to break, thus forming 2 OR groups with a free radical on the oxygen. So now the next step is to have one of the RO groups, and remember there is this free radical, react with HBr. And basically what ends up happening is that this free radical is going to form a bond with one of the electrons from this bond. Particularly the hydrogen is going to be attached here, and this electron is going to break free from this bond, thus going on the bromine, thus forming ROH as well as bromine with a free radical on it. Keep in mind, bromine also has 6 other electrons attached, and this is the molecule we are most interested in. So now the next step is to basically react this alkene with bromine which has a free radical. So when we react this reaction, what ends up happening is that the free radical ends up going on this carbon. And the reason for this is because this is going to create a secondary free radical which is more stable than a primary free radical. So when that happens, we end up creating a molecule that looks like this. Keep in mind there is a free radical here. And as you can kind of see, this is very different from the first reaction in the sense that the bromine is now added on the less substituted side so that the free radical can be on the more stable, very similar to the previous first reaction. So now the very final step is to remember that we have additional HBr in the solution. So when you react this molecule with additional HBr in the solution, what ends up happening is that we're basically going to be getting rid of this free radical like so. So specifically, this electron from the hydrogen is going to form a bond with that free radical, and this bond is going to break on the bromine. So once that happens, we're now going to create a molecule that looks like this. Right? And if you really want, you can draw the hydrogen here. I'll do so just to show you. But remember that we also have free bromine radical in the solution, which can be used to also propagate other, alkene molecules, like so. So now the last set of reactions I'm going to be teaching you is about the hydroboration-oxidation reactions. So if we have some kind of alkene, and we react it with HCOAC2 and H2O as well as NaBH4, this is going to convert this alkene into an alcohol. And something I want to point out to you is that look how this alcohol is on the secondary carbon instead of the primary. So this is Markovnikov. Conversely, when we react this alkene with BH3 and some kind of peroxide and NaOH, we're going to also get an alcohol, but this is on the primary carbon. Thus, it is anti-Markovnikov. So one good way I want you to think about this is notice how this is kind of in partially acidic solution, whereas this is in pure basic solution. And I say pure basic because we have boron, BH3, some kind of peroxide, as well as sodium hydroxide, which is all pretty basic. So because of the basic solution, this is going to give us an anti-solution. Conversely, when we react this molecule in a somewhat acidic solution, it's going to give us a secondary carbon with the alcohol. So mechanistically, the mechanism for this reaction is quite long for both, so I'm not going to show you. But quite frankly, just remember that if you have an alkene and we react it in an acidic solution, it's going to give us the Markovnikov solution, whereas if we react it in some kind of basic solution, it's going to give us an anti-Markovnikov solution.